Sorry for being late, everybody. This is gotta be one of my worst days ever. All right, let's see if I can even get PowerPoint to work. Share that.
We can see it.
Fantastic. All right. Okay. Whew. 20 minutes later. Okay, so this week about well, some more kind of measures of center, but we call these measures of relative standing. So it's basically, before we had measures of center, which were the mean, the median, and the mode. Then we had measures of spread, which were the range and the standard deviation and the interquartile range, those things. Now we've got measures of relative standing, which is basically how do the data values compare to the rest of the set. So that's what a percentile is. It tells you if this data is in the 60th percentile, it simply means it is larger than 60% of your data. Now, there's some inconsistency with percentiles where some authors will talk about the 60th percentile as being greater than or equal to 60% of your data. The more common thing is if you're in the 60th percentile, then that means you are strictly greater than 60% of the data. So if you had 10 pieces of data, and let's say just to make it easy, the numbers 1 through 10, then the number 7 would be the 60th percentile because it would be bigger than the numbers 1 through 6. So that's the idea. 6 would not be the 60th percentile because it technically only has 50% of the data values below it. It has 60% less than or equal to it, which some people would count that. But the more common definition would be that 7 would have to be the 60th percentile. So it has to be strictly greater than 60%. Okay. You guys can hear me, right?
Yes, sir. Yes, sir.
Okay. Thank you, because my headset earphones aren't working. Okay. The empirical rule. This is only applicable to data that has a normal distribution, that pretty bell curve that we've seen a million times. And if it has a bell curve, then these proportions are always true. It doesn't matter if it's a bell curve with a huge standard deviation. It doesn't matter if it's a bell curve with a small standard deviation. So if it's a really wide curve or a really narrow curve, it doesn't matter. It still will always be the case that if your data is normally distributed, then roughly 68%, it's not precise, but roughly 68% of your data is within one standard deviation of the mean. So if you go out just one standard deviation in both directions from the mean, so let's say the average is 50 and the standard deviation is 10 to make the numbers really easy. If you go up to 60 and down to 40, that's going to capture 68% of your data. And then if you go 10 more in each direction, so now you go up to 70 and down to 30, that's going to capture 95% of your data, roughly. It's close to, these are rounded off numbers. And then if you go 3 standard deviations in both directions, so now you go up to 80, right? You go from 50 up to 80 and from 50 down to 20. So from 20 to 80, that's going to capture 99.7. So you can see that damn near all of your data is within 3 standard deviations. So those little tails on the end of the normal curve is what's beyond 3 standard deviations. And that's, that's almost just nothing but outliers. Now, the whole 95% being 2 standard deviations away is kind of where alpha comes from. You've probably seen alpha set as 5% in a lot of hypothesis tests and other statistical analyses. Well, it comes from the fact that if you go 2 standard deviations in both directions, you capture 95% of your data. So that 5% that's left over becomes a really easy kind of error rate. So that's how those two things work together, so to speak. Okay, so here's a simple example, right? You've got a data set with a 40 standard deviation of 3. So what range would encompass about 68%? Well, we know we just go plus and minus 3, so there's 37 and 43. Okay, box plots are just a visual representation of what we call the 5-number summary. And the 5-number summary are the words that you see right there. The lowest value, i.e. the minimum, the lower quartile, or Q1, the median, or Q2, the upper quartile, or Q3, and then the highest value, or the max, right? So you got the minimum, Q1, Q2, Q3, and the max. And the Q's just stand for quartiles, right? So the median is the second quartile because remember the median is the value that has 50%, half of your data below, half of your data above. And if you cut your data into quarters, right, quartiles, the lower quartile is the first 25%. The second quartile would be 50%, so there's your median. The third quartile would be 75%. And then, of course, the lowest and highest, those are just your mins and maxes. Now, it depends on if you're doing a standard box plot, which is what this one is, or if you're going to do what's called a modified box plot. And when you do a modified box plot, instead of the low end and the high end being the absolute minimum and the absolute maximum in your data set, what you will do instead is those whiskers will stop at the lowest value that isn't considered to be an outlier, and the other whisker will stop at the highest value that isn't considered to be an outlier. And if you don't have outliers, then of course it defaults to the minimum and the maximum. But if you do have outliers, then it stops at whatever the highest and lowest are that are not considered outliers. And then the outliers are normally designated with just little asterisks. Okay. Now you might be asking yourself, well, how the heck do I know if something is an outlier or not? Well, an outlier is just a data value that is extremely different from the majority of your data values. So it's a lot bigger than everything, or it's a lot smaller than everything. And again, students go, well, what does it mean to be a lot, right? What does it mean to be a lot bigger or a lot smaller? Well, it's a very simple calculation. If you take this distance, the distance between Q3 and Q1, that's called the inner quartile range. And we talked about this long ago when we were talking about the measures of spread, right? This is one measure of spread where they do the inner quartile range. So you literally just take the Q3 value and you subtract the Q1 value from it, and you get that distance. And that's the inner quartile range. Now let's say Q1 is 30, and let's say Q3 is 40 to make the math really easy, right? So our IQR is 10 because we're going 30 to 40. Then what you do is you take that interquartile range of 10, you multiply it by 1.5, you get 15. And now if you go 15 from both sides of the box, right? This is called a box and whisker plot usually, or just box plot. But if you go 15 above the box and 15 below the box, i.e. 15 above Q3 or 15 below Q1, those are your cutoffs. Anything beyond those values are considered outliers. So remember, our box went from 30 to 40. So if we go up 15, we go up to 55. If we have any data values that are bigger than 55, those will be considered outliers, and we'll mark those as asterisks. And the whisker will stop at the largest data value we have that's 55 or smaller. And the same thing in the other direction, right? We go down 15 from 30. So our cutoff is 15. Anything smaller than 15 will be an asterisk. And the whisker will stop at the smallest data value we have that's actually 15 or greater. Questions on that? Okay, fantastic. The nice thing about the box plot is it does give you an idea as to whether or not your data is skewed, right? Because if your data was perfectly normal, if you had a perfect normal distribution, then everything would be symmetrical. The two whiskers would be the exact same length. The median would be right in the middle of the box. But we can see that here the median is shifted a little to the left. This whisker is a little shorter than this one. And so who wants to guess? Is this skewed to the left or skewed to the right?
Skewed to the right.
Very good. Absolutely. The longer tail is the direction of the skewness because it gets pulled in the direction of outliers. So if this has outliers, it's most likely on the higher end. And then here is a picture of it. You can see here's the normal distribution with the pretty little symmetrical box plot. And then here's one that's skewed, and here's those outliers I was talking about that they just normally put asterisks, but this one they just put little circles. And so that's skewed to the right. That'd be normal. And then, of course, skewed to the left is just going to look just like this one, but in the other direction. Okay, so here's a nice visual representation of how the box plots kind of connect with the empirical rule. We know that, if we have a normal distribution, the median is right in the middle. The mean, median, and mode are all the same thing. They're right in the middle of our distribution. And then if we go 25% in both directions, that's Q1 and Q3. So we can see that's 50% of our data. And of course, if we go a little bit further, it's hard to see, but this little mark down here, that's Greek letter sigma, which means standard deviation. So if we go one standard deviation in both directions, that's where we get 68% of our data, which of course, half of it would be 34. So you can see that the Q3 is a little shy of one full standard deviation out there. You can also see that, right, here's 50% of our data, and it's pretty tight, it's pretty narrow. And then the other 50% is much wider because, of course, the curve flattens out. So you have to go wider to get that same 25%. The area under any probability distribution is always 1. That'll come up a lot next week. But this is a normal curve. This represents frequencies of your data. This is a distribution curve. So the area under this curve actually equals 1 as well. They always do. And that goes for skewed ones as well. The area under this skewed one is also 1. Okay, scatter plots. I'm sure you guys have seen scatter plots before, right? It's just a way of visually showing the relationship between two variables. Price of peaches and the number of peaches sold. Anybody who knows anything about economics knows that as the price goes up, right, demand goes down. So as the price goes down, demand goes up, and that's why you get this what's considered a negative correlation, right? Because as the X value gets larger, i.e. the number sold gets bigger, the price gets smaller, it goes down. So it's a negative correlation. Whereas over here, we've got a nice, strong, positive correlation between temperature and ice cream sales, which makes sense. As it gets warmer, people are going to buy more ice cream. And you can see that between both of them, they have a fairly decent correlation, right? The ice cream is even better than this one. This one still has a nice pattern, but it's a little thick, right? The dots are a little spread out. Whereas this one is pretty good, right? It's pretty straight. It's almost a perfectly nice little straight line. You could fit that. So there's a real strong correlation between temperature and ice cream sales. Now here's a couple other examples that are obviously very weak correlations. You can see high school GPA and your college GPA. There is a bit of an upward trend. So you can see that people who have a higher high school GPA have a higher college GPA, which would make sense. But you can also see that, they're kind of all over the place. So it's a much wider spread. There's a much weaker correlation between those two, because there's a lot of things that go into, why someone does well in college. It's not just based on how well they did in high school, right? It depends on the degree they're taking. It's a lot harder to get straight A's, as a mechanical engineer than it is as an English major. Things like that. Could be somebody could have done really well in high school and they got to college and decided that they discovered drinking. And then, so there's all sorts of reasons why these are not strongly related, or more strongly related. And then, of course, this one, month, and barely see it. Let's see. Holy moly, that's tiny. Number of people. Oh, number of people. I wonder if that's number of people born in a month. You can see that's kind of pretty evenly spread out, or I don't even know what it's supposed to represent, but you can see that it's a pretty crappy correlation, right? That the dots are kind of all over the place. There's no real trend to them. You can kind of see an upward trend with the other one, but this one's just randomly all over the place. So you can say there's pretty much no correlation between those two variables, whatever the heck they happen to be. So here's a pretty good positive, an even better negative, and then absolutely no correlation whatsoever. Here's another example where you can see these line up perfectly in a straight line. So that's going to have a correlation of -1. These down here line up perfectly and pretty much in a straight line with a positive correlation. So that's going to have a correlation of 1. Then you can see as they start to get a little thicker. So now it's down to 0.8. It's getting even thicker, with the more spread out, but you can still see a positive trend. That's a 0.4. Same thing here. It's getting really thick, but it's a negative trend. So it's -0.3. And then when it's buckshot all over the place, it's 0. So we know that our correlation ranges between -1 and 1. The closer it gets to either -1 or 1, the stronger that relationship is. And then, of course, the closer it gets to 0, the weaker that relationship is. Which brings us to the big thing that we're all working on this week, which is the mini project, right? In addition to the homework this week, you've got the mini project, and you've got to do a box plot in the mini project. You've got to do scatter plots in the mini project. You've got to compare things to the empirical rule in your homework, right? So all of this stuff that we've touched on is going to come into play with this week's work. Okay, questions on the slides, the theory stuff that we did.
Dr. McBride, so we can pre-turn in both the mini project and the week 3 homework to you by Saturday at noon then?
Yes, absolutely.
Okay, thanks.
Stop sharing that. Instead, let's see if we can go to SAS and get SAS to work. Fingers crossed, everybody. And while that's thinking about that for an hour and a half, are there any homework questions that you guys want to go over? What was that?
Sorry, that's me trying to listen to the class with my 2-year-old sitting at the table. I was gonna say I can't remember what number it is, but it's a side-by-side box plot, and I'm getting just 2 different charts, and they're not side by side. So I don't know what I'm missing to make it look like it's supposed to.
In order to do a side-by-side box plot in SAS, what you have to do is you have to put all of your data under one variable name. So I thought I had given you guys that in your set of data. So in your set of data, you should have something called the mini project new drug data, and then there's one called mini project BP categorized. Do you guys have that data set?
I didn't see it.
I was gonna say, I'm not in front of my computer at the moment. If I did have it, I just didn't realize I had it.
Can somebody verify whether or not I put that in with the rest of the data sets, please?
I sure do not see it.
Okay. All right. Then what you're going to need to do is open your data in Excel and do a little manipulating. Or if you can figure out how to manipulate your data in SAS, which somebody had just posted to the doctoral dialogue for this week, that she saw how to do it on a video, but can't remember where that video was. And I'm hoping somebody can find it for us.
I see the new drug data in the mini project directions. Under module 2, click on mini project, action item 1, download new drug data. It's a Excel.
But I think that's just the one. He's talking about having a second one. Aren't you, Dr. M? Uh-oh. We have the new drug data, but he said he thought there was another file he sent to us.
Oh.
And I just saw the one, the new drug data.
Gotcha.
Uh-oh.
Do you think he knows we can't hear him?
Can you hear me now?
Yes.
Yes, now we can. So we only have one drug data file, one Excel file. And you're saying that you thought you sent us two. Is that correct?
I thought in that packet of files there was two, but I guess
Okay.
There's, if you go to the Google Share Drive, under you open up the zip file, the BP categorized mini project BP categorized Excel file is there.
Okay, thank you. It is there, guys. Okay.
Yeah, I see it.
So that's the one you're going to want to open. You're going to want to load that. And if you can't load it, can you guys see my Excel, or are you only seeing the web page?
Just SAS.
Okay. Try a different share. Okay, screen. Okay, now you can see Excel, correct?
Yep.
Okay. So this is what you need to do if you want to do it by hand. If you can't find the file that I put there in the zip file and so on and so forth, they're also on the Google Drive. If you just go to the it's got week 2, week 3, and I believe there's a folder that just says projects, and it should be in there. But anyhow, what you need is you need all of the BP scores in one variable. So you can see I just have a variable called BP, and it has all of these scores. And then you need what's called a categorizing variable. So I have a second variable called BP cat for BP category. And these all are the before, right? We had two variables in the mini data set. We had BP before and BP after. It was basically they measured people's BP before they did something and after they did something. I think it was when they took a drug to mess with their blood pressure. So these were the blood pressure readings before they took the drug. And then as you scroll down, you can see that all of a sudden it turns to after. These were all the readings that were taken after. And then that's the data set you have to use in SAS in order to get a side-by-side box plot. So what you have to do is you have to load that data set, right? Or, change it yourself or whatever. So I'm going to load the BP categorized one, let it run. I like to check my output data, just make sure I've got what I've got. Yep, so here's my BP variable, here's my BP cat variable. And then now if we go to our tasks and graph and box plot, and grab the BP data. So your analysis variable is now going to be BP. You'll see that it only picks BP because it only lets you pick a variable that has numbers in it. And then your category variable is where you have to add in the BP category. And now if you run it, it will give you a side-by-side box plot, just like that. Now, I don't know about you guys, but I prefer my box plots to be horizontal, which I thought was something you could change here somewhere. Somebody had figured it out.
Right there.
Thank you, plot. Yeah, horizontal. There it is. And the only reason why I say horizontal is better and makes more sense is because so Catherine, go to the Google Drive, our normal Google Drive, and there's a zip file there. It's our data file zip file. And it's amongst there. You can also just go to the Google Drive, and it should be in there under projects. So let's see. 7. So data sets, data files by week. Under here, project files. You can see final project, final project, final project, final project. Then here's the mini project new drug data, which is just the whole set of data that you need for all the other questions. And then here's the BP categorized one you need for that question. Okay, so that's the easiest place, right? If you've already kind of done the zip file and downloaded all the other stuff and then uploaded them all to SAS rather than dealing with the entire zip file again, if you don't have it anymore, is you can just download this data set and then upload it. Okay, so as I was saying, the reason why I think it makes more sense to have your box plot horizontal is because then it looks like a number line, right? They're sitting on a number line. And it's oriented the way a number line is. It goes smallest to the left and biggest to the right. And so now you can see which of the two groups, right, is how it relates to the other. So here's the before group down here. Here's the after group up here. So we can see very quickly and very easily that after they took the drug, their BPs all pretty much fell, right? You know, the max is lower, the Q3 is lower, the median is lower, the Q1 is lower, the min is lower. The entire box plot is basically shifted to the left. So that would be, you know, something that you could discuss in the mini project as to, you know, what you see from the data or whatever. Okay, so that's the box plot one. What else you guys got?
If nobody else is going to go, I'm going to keep going. When I did the scatter plots, there's a part on down the mini project that talks about scatter plots and finding the correlation. I don't really see a correlation when I do them. So I don't know if that's the answer. There is no correlation, but that just doesn't seem likely for this project.
Everything has a correlation. It's just the correlation could be super weak. So there is a correlation. When you run scatter plot, it does not give you the correlation. You have to do one of two things. You either have to just run the correlation
analysis
function or analysis, yes. Yeah. Or you can run the linear regression function, which will give you both the correlation and the scatter plot. But running linear regression, that menu is not as simple as just running a scatter plot and then running correlation, which is what I would suggest, because it's really easy to run scatter plot, right? I mean, I'm sure you've all figured out if you haven't even looked at it. It's really simple. It's like any of the other graphs. You know, you choose what variable goes on X, you choose what variable goes on Y, you basically run it, and blam, it gives you your nice little plot. And then when you want to figure out what the correlation is, you just go to, I think it's statistics, and do correlation analysis. And if you run correlation analysis, here it says analysis variables. So what you do is you just add both variables together. So whatever you're trying to correlate, when you go to add, you just highlight both of them and then hit OK and load them both. So you can load multiple variables into this box and then just hit run, and it goes that way. And it gives you the correlation between all those things. I don't think you have to put one here and one in correlate with, but try it one way or the other. But I'm pretty sure if you just put them both in analysis, it gives you a little box. And shows you.
I did it with one in analysis variable and one in correlate with, and I got a number. It didn't give me any errors or anything. So am I to assume then that was okay, or better off to do it the other way?
Yeah, it sounds like it's fine. Let me see if it works both ways. Let me try this one. Doesn't work. All right. Data. Well, that's BP categorized. That's fine. Whole mini project. Do. Here. Analysis variables. I thought you could just do both of them. Let's see what happens. Yeah. So what it does is, here's the BP before and the BP after, and then here's the BP before and the BP after. Now let's see what happens if we change it. So 0.19. And then let's put it down here. BP after. And run it that way. Same thing. 0.19, right? BP before versus BP after. What this does is it allows you to compare correlations between a lot of things. So, for instance, I'm here for this, and let me show one. So now I can let's put in age and BP. So now we're going to get a 3x3 table. So this first square is the correlation between BP before and BP before, which of course is a correlation of 1. Then the correlation between BP before and age is 0.12, and then BP before and BP after, right? And then age and before, age and after, right? You obviously get the same things just written over and over and over again, but it's just a quick way to get a table of all of them. So now you can see how everything correlates to everything else, kind of thing. Okay, what else?
Yep, this is Lonnie. Question on the 5, I think it was the 5 summary.
5 number summary?
Yes, I'm somewhat confused on that one.
The 5 number summary is minimum, Q1, median, Q2 or Q3, and max. So if you go to summary statistics and load your data, so I'm just going to run it on age, and then go to your options. You want the mean. Sorry, I think if it just wants the 5 number summary, you want min, max, median, and then under additional, nope, it's under percentiles. And then under percentiles, you've got lower quartile and upper quartile. And those will be your 5 numbers. You can see there, it just lists them all out there. And if you run that, there's your 5 number summary. So there's your min, there's your max, there's your median, your lower, and your upper. Now it's not in the correct order, right? 5 number summary should go minimum, lower quartile, median, upper quartile, max. And if you went to the code and did edit, you could get it to do that by just rearranging the order in which these are written. right? So you want minimum, and then you want Q1. Then you want median. Then you want Q3. Then you want max. And I'm just going to get rid of everything where it's written. So there we go. We got min, Q1, median, Q3, max. And if we run this one, now it's in the proper order. But of course, you could also just take those and put it in your own little pretty table if you wanted to. There's also a way to get rid of all those extra zeros in the code. And I think it has something to do with maybe var def or something like that. I can't remember off the top of my head, but there is a way to tell it how many decimal places to give you if you want to play around with that as well. Okay, what else?
Are we staying on the mini project right now, or
you can do either homework or mini project?
Okay, I had a few homework questions if everybody's okay with that. It was 330 part C, and trying to get to where I was on here so I can say exactly what my problem is. Oh yeah, it's like a really scary, I don't know, it's got a lot of symbols in there that are kind of freaking me out.
Oh yes, okay. So this is just ugly math speak for the empirical rule. So y hat, that, or y bar, sorry, the little bar above y just means the average. So this is the average of your data values. For some strange reason, they're calling them y's instead of x's. So all of these data values, if you calculate the mean of these data values, that's going to be what they call y bar. We normally call it x bar because we normally refer to these as x's instead of y's. But anything with that straight line over it just means a mean. So that's the mean of the y values. And then we use that to estimate mu, the Greek letter mu, which is the mean of the entire population, right? So regular letters are what we get out of the sample statistics, and then Greek letters are the parameters that we get for the population. So we always use the statistics to try and model or estimate what's happening in the population. All of this junk just says, take the mean and go plus and minus S. Well, S just means the standard deviation of our sample. And if we had the standard deviation of our population, we would use the Greek letter sigma. So S for sigma. So this first interval is just going to be the mean plus and minus that, and then the mean plus and minus 2 times it, and so on and so forth. So let me scroll down. You guys can see my page, right?
Yes.
Okay. So let me just give you some numbers so you can see what I mean. Let's pretend that the mean equals 20, and then S, which is our standard deviation, equals 5, okay? Then that first interval where they say basically the mean plus minus S, right, is just going to be the interval of 15, comma, 25, because it's the mean minus the standard deviation, so 20 minus 5 is 15, and 20 plus 5 is 25. And then the second one is going to be the mean plus or minus 2 times that, so you're going to go up and down 10. So that's going to be 10, comma, 30. And then, of course, the last one, where you go plus or minus 3 times those, would be 5, comma, 35. That's it. That's all you're doing for that part, is you're finding those intervals, and then you're calculating the percentage of your data within all those, right? So after you calculate the mean and the standard deviation for your data, then you can calculate these 3 intervals. Then you go back and you count up how many data values are in each of those intervals, and then figure out what that is as a percentage. right? Because this is a total of what, 70? It's like 70. I think it's supposed to be 50 by 50, not 53. 70 squares were randomly selected, right? So here's 70 pieces of data. So let's say in your first interval, let's just pretend that it was between 15 and 25, which obviously wouldn't work at all with our data because our numbers, go from like 4 to 10 or whatever. But if you count it up in here, and out of those 70 pieces of data, 20 of them were in that interval, then you would go 20 divided by 70. You would figure out what that was as a percentage. And then you would say, okay, so here's the percentage of my data values that fall in this first interval. The empirical rule says it's supposed to be 68. Mine is really close, or mine is way off, whatever. That's what it means when you're supposed to count it up and then compare with the empirical rule. Does that make sense? That answer that question for you?
Yes. And it's good that we're recording this. I think I'm gonna have to go back and listen to it again, but it did make sense at the moment.
Good. Okay. What else?
I had part A on 3.34. It's the stem and leaf plot again, and I had trouble with this on the last homework, and I'm doing what I think I fixed last time, but it's presenting a new problem. So
okay,
this may be, and the weird thing is it's not showing me any errors this time. Remember last time I sent you the errors, the screenshots, and it has no errors. It just won't produce it for some reason.
All right. So I always say start from scratch. Go back and reload your data. Make sure your data is loaded. So I've got the data for 334 loaded. And I check and see, okay, all I have is basically this rates variable. And, make sure you know where it loaded. So it's an import to. So now I can go to my tasks and my graphs, and I'm just going to pick histogram. So it's a simple code, right? And hit edit and copy all of this and delete it just to start fresh. Okay, so now if I go to the SAS how-to guide and scroll down right here, create a stem and leaf plot. I'm just going to copy all of this, Control C, SAS, Control V. First thing I need to do is always change your data call out so that it's pulling the right set of data. This one was put into import to, so I need to change that to import to. The next thing I obviously need to change is my variable names, right? Because I'm no longer using the year data that we had for question 310. The variable here is just rates. So I can program. Then this needs to be changed to rates. And I can get rid of all of this. Okay, let's just run it and see what happens. There we go. There it is.
Okay, I think I was just trying to change bits and pieces. So I'm just going to rewrite it all.
So the things to learn from this class as far as SAS is concerned, if you're going to do any kind of programming, there are certain key elements that you always have to pay attention to in your program. The first thing is your proc statement. Proc stands for procedure, and it tells SAS what kind of procedure you're going to run. In this case, we're running the univariate procedure. The second thing that is super important is your data call out. You always need to, so, and the reason why I point these things out is because anybody who works in SAS and does things regularly in SAS will always have their version of this SAS how-to sheet. I still have one from when I did all of my SAS crap for my dissertation, 15 some odd years ago. Oh God, I think it's closer to 20 now. It's so damn old. But it has all of the code that I used for my dissertation on it. And if I ever wanted to go back and do something else with SAS, do the same kind of analysis with SAS, but with a different set of data, I could copy that code over. And really the only thing I would have to change is I would have to change my data call out, because I'd have to make sure that I'm now calling out the new data set that I'm using. And I would have to change my variable names, because obviously my new data set is going to have different variable names than my old data set. And the rest is kind of a skeleton that you can play around with. And that's just something to think about if you do want to keep these, these coding snippets and use them later. Okay, anything else?
Last one for me, part C on 3.56.
Okay, 3.56. Is part C. Okay. So this is kind of similar to the question we had last week, where you had all those different groups and you guys calculated the means of all of the individual groups. Then you calculated the mean of the entire set of data as one. And then it asked you if there was a way that you could get the entire group from the individual groups. And you could do it by calculating a weighted mean. So you take each group's mean and you multiply it by the size of that group. And then you do all that and you add them all together and you're good. Well, here they're trying to get you to do the same thing with a standard deviation. And quite honestly, there is really no technique that works really well for this without a very complicated formula for it. But basically, your best estimate is to take the standard deviation of each set, square it, so it becomes the variance, multiply it by the sample size minus 1, so the sample size of each of the things minus 1. Then add all those together, divide all of those by the entire set size minus 1, right? So add all these together and say, okay, there's 70 total, so it'd be 69. And then take that answer and take a square root. And that'll get you pretty close to what it needs to be. But it's kind of a silly question. I wouldn't worry about it too much. I don't know why it's there. I keep telling them to get rid of it.
Okay, I was just writing what you were saying furiously.
Yeah, it's basically just each standard deviation squared. You square each standard deviation, which turns into a variance. Then you take each of those variances, you multiply them by the corresponding sample size that they came from minus 1. So this first sample, let's say, is 20. I don't have time to count them. Then you would multiply it by 19. This second set, let's say, is 27. You'd multiply it by 26. This third set is 15. You'd multiply it by 14. This set 4 has 12. You'd multiply it by 11. The last one has 10. You'd multiply it by 9. When I say it, I mean the variance of each of those sets. So that's just the standard deviation squared. Once you've done all those multiplications, you add all those numbers together. And then once you have that sum, you divide it by the entire set size minus 1. So you add all these numbers together. So the 20, the 23, the 15, the 10, and so on and so forth. You get how big your entire set of data is. You take that number, subtract 1 from it, and that's what you divide that big sum by. And then that final answer, so you've summed everything up, you divide it by, let's say, 72, because there were 73 total pieces of data. That final answer, then take the square root of it, and that should be pretty darn close to your standard deviation.
Awesome. Thank you.
Yep. All right. What else?
And we continue to use the our program of choice for the mini project.
Yes. Just like everything else in this class, if you want to use SPSS or Excel or whatever, you're fine.
Great. And do you happen to know if that same if that same option applies to Math 810?
Well, I know that as far as the school is concerned, they no longer require students to use SAS in any of their classes. So yes, it should apply in 810. But as I've warned before, the person who teaches 810 might not be able to show you how to do anything in anything other than SAS.
Okay, thank you.
Okay, what else?
Can you discuss 3.69b?
Sure.
I went through it and it just doesn't look great to me.
Well, it should be a pretty crappy correlation. It should look pretty much, well, let me see. It's going to look like that. It's got these really bad outliers. It's got a bit of a trend to it. But if you're getting something that looks like this, then you're not doing it wrong. This is pretty much what it looks like. And the correlation is not that great. I take that back. That's a pretty strong correlation, 0.8. It's the other one that's really weak. I think this one's terrible. When you do in 380 part A and you do this scatter plot, you can see this is total buckshot. It's absolutely no correlation whatsoever. And it has a correlation of 0.4. So even something as scattered as that still has what some might consider a decent correlation of 0.4, but really 0.4 is a pretty darn weak correlation.
Okay.
That slide that I showed you where it showed the buckshot and it's a correlation of 0. It's pretty damn impossible to get a correlation of 0. I mean, mathematically, you can find a relationship between anything. It's just going to be a super weak relationship. So the idea of getting a correlation of 0 is really more of a theoretical thing. It never really happens with real data, but you will definitely get, correlations down in the 0.4, 0.3, 0.2, even 0.1 kind of stuff. And those are super, super weak correlations. Does that clear it up for you?
Yeah, I got the scatter, the plotting portion was real. I mean, it was almost like in the corner, and that's exactly what you pulled up. And I was like, oh gosh.
And it's because of those outliers. If you went in and figured out where the outliers were and cropped them off, and in fact, if you I think if you have it in SAS, if you have the output in SAS, I thought you could figure out where the outliers were. Like if you hovered over them, it popped up and it told you what the numbers were. And if it doesn't, then you could kind of go through your data and you could find them, right? Because all you're looking for are syphilis scores, at basically 3,000 and above. If you could just lop off, basically remove these 4 pieces of data, then this would look a lot better. It would spread out and it would look much better in a graph. Now, I'm not saying you should do that, and neither should you do that now or ever, right? Because you don't just get rid of data to make your results look better. If you were going to do this and present it to somebody, and it was going to matter, then you could do this, and then you could lop off the 4 and show that graph as well, explaining that I've removed the 4 outliers and list those 4 values because they're outliers, right? So I wanted to see what the data looked like without the outliers, that kind of thing. But then when you talk about, why are they outliers? There's 2 reasons why data can be outliers. It could be because it was a measurement mistake. So for instance, when you were getting the data, somebody keyed the numbers in wrong, or somebody filled out the form wrong, or that kind of thing. So it's a measurement error. Or they could be outliers, meaning that the data values were true, they were what you got, it just happened to be oddball results. And it's usually, you usually don't want to get rid of outliers that are oddball results. You only want to get rid of outliers that you're fairly certain are from measurement mistakes. Because then otherwise you're basically you're combing the data and you're trying to make things look the way you want them to look, and that's bad. That's not what you're supposed to do. Okay, anything else? We all good? Homework and mini project, we're good to go?
Oh, there'll be more questions, I'm sure.
Yeah, I'm sure there'll come up more questions on Friday. Okay, well, we started late, so we ran late. Sorry about all the technical glitches. At least on Friday, I will be back home with my more reliable desktop, so this should not happen again. Thank you all for your patience. I'm glad that you could stick around. I will try and have this link up quickly, but being the laptop and all that. What I did this time is I asked it to save it to the web. So a link to this recording should show up in our Zoom link in our classroom. So if you go to the Zoom link in our classroom and then go to cloud recordings, it should show up within an hour or two. And it'll stay there for the entire time that our class is running. And then what I'll do is I'll download it and then upload it to my YouTube channel so that I can put a copy of the link in our Google Doc, because after a while these do get purged, which is why I've put them all on my YouTube channel, because then they'll stay there as long as I want them and not as long as Zoom wants them. So your cloud recording for tonight should show up fairly quickly under this tab, and then it'll show up on our document, probably not until Friday when I get home and have a chance to download it and upload it again. Okay, any last minute questions before we go?
Yes, overall, how is the course, how is the cohort doing in your estimation?
So far, I think you guys are all doing really well. I mean, the grades that I've seen, I mean, we've only had basically one set of grades, because I haven't been able to grade your week 2 homeworks for the most part yet. But yeah, I think you guys are doing great. You're definitely more collaborative than I've seen a lot of other cohorts, which is always a good sign. So I think you guys are doing well.
Okay, good. We'll keep trying to do our best.
Yeah, absolutely. And on that note, there's probably a good chance I will not get most of your week 2 homeworks graded until Friday as well, because this laptop is just not my friend.
Okay, thank you. Good luck. We'll
Yep.
see you then, Friday.
See you guys on Friday.
Okay, Doc. Thanks a lot. Have a good night.
Good night, everybody.
Thank you.
Thank you, Doc.